So onto is surjective. Now a mapping that is both injective and surjective is called bijective. Bi for two. So two conditions are satisfied. Right? So what Sipser's calling correspondence, I've heard that used somewhat. I don't know if that's his more so, or he's picking it up from a tradition within computer theory, possibly. Anyway, so the standard mathematical term for what Sipser's calling correspondence is bijective. So you have a bijection. That would be the noun, and the adjective is bijective. Function can be bijective, so that means it's one-to-one and onto. Or using the standard math terminology, a function or a mapping is bijective if it is both injective and surjective. Okay, so a few terms there you need to memorize. Right? So spend a bit of time on it. All right. Now, in a correspondence or a bijection, each element of set A maps to a unique element of set B, and vice versa. If it's bijective, see, that's what I'm used to. If it's a correspondence, you can go back and forth between set A and B. If you start with little element A of your set big A, that will map uniquely, just to one element in your big set B. There'll be element little b, let's say, in set big B. So it's one. You can go back and forth. There's no ambiguity. And it's clear which is, so in other words, they're pairing off. They're paired off. The elements of set A and the elements of set B have paired off. Like you could imagine set A is a set of women at a dance, and set B is the set of men at a dance. And let's assume that the number of women, number of men equal, or number of dancers, the people. And so when the music starts up and everyone's dancing, male with female, then you have a pairing, right, of those two sets. Imagine it that way. All right. Okay. So here's the critical point for Cantor. Remember that two sets are the same size if you can pair them off effectively. Even if the sets are infinite, if you can pair off one infinite set, if you can create a correspondence, if you can create a bijection between two infinite sets, then according to Cantor's definition, those two sets have the same size. Okay? Size, I guess, in inverted commas, because you're certainly not counting the number of elements. You're not defining size in that sense. All you're really interested in is the relative size, the absolute size, but that has no meaning for infinite sets. You're just comparing the size of one with the size of another, two infinite sets, and they are said to have the same size if there's a correspondence between them, a bijection between them, a pairing between them, a one-to-one onto mapping between those two sets. Okay, lots of ways. This notion of function between two sets is so basic. It has many names, used in many branches of mathematics. Personally, I'm used to injection, surjection, and bijection. That's the standard. They're the standard terms used in, say, algebra, abstract algebra. All right. Well, let's now use that notion of pairing in an example. So 4.13, and we'll have two infinite sets. One's just a set of natural numbers. One, two. Like the kindergarten kid knows. 1, 2, 3. The counting numbers, if you like. 1, 2, 3. ... And so that's obviously an infinite set. Call it, it's n. That's the usual symbol in pure mathematics. Capital N is the infinite set of natural numbers. Natural in the sense it's probably the kind of numbers that's the most natural, because little kids understand, the notion of 1, 2, 3. They can count, right? Kindergarten. And epsilon here, capital epsilon, let's say, let that infinite set be the set of even natural numbers. So not 1, 2, 3, that's n. So epsilon, we could call it 2n. So it's 2, 4, 6, right? The even positive integers. Okay, now, according to Cantor's definition of size, those two sets, even though they're both infinite, they have the same size. Why? Well, because you can form a correspondence between them, or using the pure math term, there is a bijection between them. There's a one-to-one onto mapping between them. There's a function between them. In fact, the function f, so if n is any member of these, the corresponding or paired member of the second set, it'd be one of these members, is just twice 2n. So there's your sort of a numerical relationship. There's your mapping, and it's obviously 1 to 1, right? For one value, n, you'll have a corresponding single value in the second set. Well, that's just 2n, right? So here it is in sort of table form. So now you can see it's just 1 to 1 and onto. All of these get mapped to. So there's a pairing going on. And therefore, by definition, given this correspondence, this bijection, this pairing, whatever you want to call it, because of that, therefore these two sets, n and capital epsilon, they have the same size in the Cantorian word, I guess, sense, the meaning, the definition of size. Right? Now, that may seem a bit bizarre, okay? Because, intuitively you'd think that this set, capital epsilon, because, every odd one's missing, right? Compared to this one. So your intuition would tell you that this set is bigger than this one. But according to Cantor's definition, the pairing, they're the same. They have the same size. Well, relative size. Okay? So, even though epsilon, capital epsilon, is a proper subset of the natural numbers, okay? But since you can pair each member of this, you can pair it off with a member of n. It's a one-to-one onto. It's a bijection. Because you can do that, then according to Cantor's definition, these two sets have the same size, right? So there's an example. All right, now here's another definition. We're introducing a technical term now, countable, able to be counted. What does that mean? Well, here's a definition for it. So definition 4.14. A set is countable, by definition, if, and there's two ways you can count a set. That set is countable if it's finite. Well, then you just count the number of elements in it. That's trivial. Okay. So if you have a finite set, it's obviously countable. I mean, in the usual meaning of the word. Okay. And the other way you can define a set to be countable is that so if it's not finite, well, therefore it's infinite. Okay. And you can say an infinite set is countable if that infinite set has the same size as n, big N. In other words, you can pair off the elements of that infinite set with the natural numbers, or the counting numbers. Natural numbers, counting numbers, same thing. Okay, that's why the word countable was chosen. Well, I guess. Okay, so if I'm talking about a countable set, it's either a finite set or it's a set that has a bijection with the natural numbers, or it's a set that has a correspondence with the natural numbers, or you can pair off the members of that infinite set with the natural numbers. Right? They're all different ways of saying the same thing. Okay, now here's another example. We're going to show that the set of positive rational numbers is countable. Okay. So it's an even weirder example. Okay, now in pure math, the standard symbol for the set of rational numbers is Q, capital Q. Right? The set of integers is capital Z. The set of natural numbers is capital N. They're the main ones, I think. Right? Okay, so by definition, three bars here. The set of what are we doing? Set of positive rational numbers. So M over N. So M and N belong to the natural numbers. By the way, some mathematicians include 0 in capital N. Well, there's nothing. I think that's a mistake. There's nothing natural about 0. Right? It took thousands of years to be discovered. The Chinese never discovered it. They had to import it. I think it was discovered in India. There's nothing natural about 0. So the natural numbers start at 1. Okay. So assuming that your n here cannot be 0, because you don't want to be dividing by 0. You got a problem there. Okay. So assuming that your natural numbers start with 1, 1, 2, 3, ... Then your set Q, by definition, is the set of these proportions, these ratios of M over N. And M and N are both natural numbers. Okay? And that the set of those ratios, M over N, by definition, that's Q. So Q is just the set of positive rational numbers, and obviously an infinite set. Okay? And we're going to show that the size of Q and the size of N same. It may sound truly even stranger, even more bizarre, but we'll show as possible in the next session, in fact, how you can form a correspondence, a bijection, a one-to-one onto mapping between these. They're the elements of Q and the elements of N. Okay, you can do that. We'll do that next session.